right, 4.3, we're going to be looking at fundamentals of biomechanics. Now, biomechanics is such a large topic in sport and exercise science. You guys can see in your workbook, I've given you the outcomes of this unit. Now, we're going to be looking at a wide range of principles here, but the good thing is that we don't need to go into that much detail. So it's about breadth rather than depth. We're going to be looking at everything, but I'll tell you what we need to know and to what level here. So let's first start off by talking about some fundamental definitions. Now, there's some key terms within the unit, but firstly, we need to know the difference between scalar and vector quantities so that we can apply this to those terms. Now, a scalar quantity is a quantity with magnitude, whereas a vector has magnitude and direction. So a vector is just a little bit more complicated than a scalar because it includes this directional component as well. So you can see we've got some examples in the pictures below. Mass, for example, is a scalar quantity. So mass is like how much you weigh. 75 kilos is your mass rather than your weight. I know that's confusing because I used weigh there twice, but your mass, if we're talking about body mass, would be 75 kilos, let's say. Whereas your weight is the mass times the gravitational force of your body, and weight is actually measured in newtons. So someone of 75 kilograms mass would actually be somewhere around 700 newtons. So we don't actually often use the true definition of weight when we're just talking day to day. When someone asks you, what's your weight? You'd give them the mass response. Interestingly, if you think about your scales in the bathroom, when you stand on your scales, that shows your quantity in kilograms. So even though your weight is measured by the scales, so the scales on the ground are measuring your mass times the gravitational force, there's a calculation that happens inside the scales, and the output that it shows you is actually mass in kilograms. So little things to think about there. Speed versus velocity. So velocity and speed are generally the exact same thing, except with velocity we've got the direction as well, whether that's north, south, left or right, up or down. Vectors always include this directional component. So let's have a look at some of our key terms now. So a force, which is shown by the capital letter F, is a push or pull acting upon an object. For example, gravity is a force, and force is measured in newtons, and it's a vector quantity. So it's the mass of the object plus the gravitational force is measured in newtons, and it's a vector quantity. If we think about distance is super simple. It's the length of space between 2 points, and it's measured in meters, and it's a scalar quantity. It's point A to point B. Displacement is the change in position of an object in a specific direction. So think about like the start and finish point in terms of displacement. And it's measured in meters plus the direction as well, which makes it a vector. Whether that direction could be north, south, up, down, left or right. So distance and displacement, people often confuse the two. The easiest example I can give you to differentiate between these terms is a running track. So for example, if I was to run 100 meters on this running track, I'd start somewhere down the bottom and I'd just run straight until 100 meters and I'd finish down the bottom as well. So in this case, the distance I've run is 100 meters, and my displacement is also 100 meters. So from my start point to my end point is 100 meters. If I was to run 200 meters, so I'd start at the bottom of the track and I'd run around the turn and finish at the top of the track, my distance is 200 meters. However, my displacement from my start to my finish point may only be 100 meters, right? So displacement is the shortest route between the start and the finish point, whereas the distance is the entire distance that you've moved. Another example here, so we've got point A and point B, Out of these three paths, path 1, 2, or 3, which one best displays the displacement? So have a think about it. Displacement is the shortest point from the start to the finish. So path 2 would be our best representation of displacement. So if I ran down path 1 from point A to point B, I might have run 300 meters, but my displacement is actually measured through path 2, which is only 200 meters, let's say. In path 3, I might run 500 meters through this path, but again, my displacement will still only be 200 meters from point A to point B. Another few important definitions that we need to know is speed. So speed is the rate of movement measured in meters per second, and it's a scalar quantity. Whereas velocity, these two are often confused as well, is the rate of change in an object's position with direction. And it's measured in meters per second plus direction. So it's got a directional term there as well, which makes it a vector. Now, speed and velocity, I'll give you a big hint here. Essentially, they're the exact same thing, apart from that velocity has got a direction within the unit as well. But they're the same, right? And they're used interchangeably, speed and velocity. Acceleration is the rate of change in velocity, or the rate of change in speed, if you wanted to say it like that. It's measured in meters per second squared. So acceleration is, think about like the change in velocity over a period of time. So I want you to think about like a 100-meter sprint again. We'll continue with that example. Usain Bolt, his top speed for a 100-meter sprint, I think, is 27 meters per second. Now, he doesn't start off the blocks at 27 meters per second. He might start at 10 meters per second, and he begins to accelerate over the course of the race to hit his top speed of 27 meters per second, which generally happens about 50 to 70 meters within a 100-meter race. So the acceleration is that rate of change in speed. And we've got acceleration, of course, as we're getting faster, and then deceleration if we're slowing down. Now, momentum and impulse, they're a little bit more confusing, but they're really important to understand because they're going to keep coming up within this unit. So momentum, you might have heard that term before. You might have said it when you're talking about, your favorite soccer team who just keeps getting better and better. They've got good momentum. They're going to win the World Cup or whatever it is. So, and that sort of definition of momentum actually comes from its true definition that we're seeing here. So momentum is the product of an object's mass and velocity. So it's a measure of the quantity of motion an object has. So as an example, let's say we have two people and they're both the same weight, the same mass, right? One of them is running at 20 meters per second and the other one is running at 10 meters per second. The one moving at 20 meters per second is going to have the greater momentum because they've got the greater velocity. So if mass is the same, the person with the greater velocity is going to have more momentum. Think about rugby as an example. Now, the guys who are the forwards in rugby are generally a lot bigger than the guys on the wing. So they're much bigger guys. They don't have to run at such a great velocity, such a great speed to generate momentum because their mass is higher. So because they're big, football players at the front there, they could run a little bit slower and still make really large amounts of momentum. Okay, impulse is the second one. So impulse, these are both vectors, by the way, because they include some sort of a directional component. So in momentum, we already know that velocity is a vector, making momentum a vector as well. And impulse, force is a vector, making impulse a vector as well. So if they've got a component within them that's a vector, they're going to be vectors themselves anyway. So impulse is a product of force and time. It's the amount of force that's applied for a period of time. Now, an impulse, another way to think of it, is the change in an object's momentum, and it's calculated as that product of force and the time over which it's applied. So I've got an example here with golf. So when you do a follow through in golf, the time is the amount of time that you're in contact with the ball, and the force is obviously the amount of how hard you're going to hit it. If we keep in contact with the object for longer and we apply more force through it, we hit it really hard, we're going to increase the impulse within that ball, therefore increasing the output of that shot. In boxing, another example, the impulse delivered by a punch, it depends on the force of the punch, the force applied, and the duration of contact with the opponent. So how long your hand is in duration with the opponent when you punch them. So it's not like a little jab is not going to have as much impulse as like a big hit. I'm not sure of the exact terminology of the different punches in boxing, but if we can keep the hand in contact with the person for longer and generate force with that, we can increase the impulse there. All right, we're going to move on and now have a look at some different graphs in sporting actions and how to analyze them. There's a few that you guys need to be aware of. So the first one is a distance time graph. So if we first look at the y-axis, we've got distance there. So as the y-axis goes up, that's the distance increasing. And we've got time along the bottom on the x-axis. Time is increasing as we move along that axis there. Now, if we look at the three lines within our graph, if we're looking at time and distance on our axes, we can assume that the line is actually showing speed. So the line is showing us the speed that we're moving, how, distance over time gives us speed. So that's the outcome. Now, if we look at the first blue line, we've got a perfectly sort of diagonal line going straight upwards. This is showing us a constant, steady speed. So the person is moving at the same speed over time. The distance is increasing at the same rate as time is passing. So they're maintaining their speed. If we look at the red line, we've got that diagonal increase there showing us a steady speed. So speed is just staying at the same level as we're moving over a certain distance. If we've got the flat line, which says stationary there, we can assume, look, that as time is going on, there's no change in distance. So this person must be stationary. And then when we've got the red line returning back down to the axis there, we've got returning to start. So the distance is now decreasing. It means this person must be running back to their starting point or returning along their path as the distance decreases. In the green line, we have an arc. Now the arc shows us an acceleration, that they're getting faster, that they're moving quicker than they were at the start. So whenever we see a curved line in a distance time graph, that shows us an acceleration there. So they're increasing as time goes on, distance also starts to get quicker and quicker and quicker, showing acceleration. We also need to have a look at some velocity time graphs. So if we've got velocity on the y-axis and time along the x-axis, if we take velocity over time, that gives us acceleration. So that line, the output, is going to be showing us acceleration. Now the first graph has got the line going horizontally straight across. So over time, the velocity is staying the same, showing that there's no change in acceleration. This person is moving at a steady speed, so they're not increasing or decreasing their velocity as time goes on. In graph number 2, we have a diagonal line, a straight diagonal line there. So as time goes on, the velocity increases at a steady rate. So we've got steady acceleration, where the acceleration is increasing at the exact same rate over time. So think like putting your foot down in a car, and as you press down, you're going faster and faster and faster and faster and faster. You're increasing your velocity, you're accelerating at a constant rate. Versus the third graph here, where we have velocity over time, and this shows increasing acceleration. So as time goes on, that velocity increases exponentially. So velocity gets bigger and bigger, showing a increasing acceleration. So think when you come off the blocks in a running race, you start off, you're gaining your velocity, and then as you've got that momentum and you're traveling forwards, that velocity begins to increase exponentially, showing this increasing acceleration. This might also be what you experience with skiing, so your velocity increases more and more over time as you start to go down the hill. We could also look at it in this type of a way. So in this case, the velocity is increasing with time, and then the velocity starts to sort of slow down as time goes on. So this person is still going very fast at the end of this graph. The velocity is still quite high, but they're not gaining speed like they were in this example here. So the speed starts to sort of top out. All right, and then the third type of graph you need to know is a force time graph. We're going to look at a few different examples of these, but force time graphs are really important for you guys to have a look at. I've heard that they come up a little bit in your exams, so important that we grasp these. Now we've got force on the y-axis and time along the x-axis. And you can see the line that's been plotted in this graph, and the area under that line is showing us the impulse. Now, impulse, remember, it's simply a measure of the force applied for a specific time. So impulse is the outcome of force and time. Impulse equals force times time, and it's measured in Newton seconds. So it's an important concept in many different sports, especially sports with some sort of a throwing or moving an object type requirement, and they require the athlete to apply a large force for as long as possible. So the area underneath the plotted line gives us the impulse. So for example, when we're hitting the golf ball, like in the example I showed you guys before, the athlete needs to strike the ball as hard as possible to apply a large force, and the ball's going to fly off in a very short amount of time. So the ball's not going to stay on your club for very, very long. It's going to hit the club, there's going to be a short little follow through there, and it's going to fly off. So we can't do much in order to change that time. We can do our follow through, but still it's not going to have that big of an impact. But we can change the amount of force and how hard we actually hit that ball to increase the impulse. If we think about another example, like a discus thrower, so a discus thrower needs to apply a force to the discus for as long as possible. They're going to try and put the most amount of energy that they can into that discus by spinning around in circles before they throw it. The same is true for javelin. So the longer sort of pull and hold they can apply to the actual javelin, the faster it's going to leave the hand. So the longer they can sort of wind up that implement, the greater the impulse and force it's going to be. I've got a video for you guys to watch on this type of a graph up in your resources as well. So let's have a look at the next step further on a force time graph. So this is a vertical jump graph. It's showing us force on the y-axis and time along the x-axis. So when an athlete does a vertical jump, so they're standing, right? What happens in a vertical jump? They're standing, they lower down a little bit into a bit of a squat, and then they burst up with as much force as they can, and they jump off the ground. So it's sort of like they're standing, they do a little dip and jump. So when they're standing still, it's only the weight from gravity that's acting down. As they bend their legs and they get into that squat position to jump up, before they jump, the force on the ground is going to be negative. So it's going to go below the line, so showing negative force. And when they explode upwards into the jump, the force becomes positive again. You can simulate this on your bathroom scales if you wanted to give it a try. So if you stand on your scales, I want you to suddenly allow your body to drop. So drop into a little squat, bending your knees, and you'll observe that the weight on the scale will momentarily sort of deflect downwards. It will drop and then come back up. And that reflects a drop in the ground reaction force that we're seeing in this graph here. So if you stand on the scales and quickly bend down, if you look really carefully, you'll notice that the scales drop a little bit as well, and then they come back up. Now, if you're in your squatting position and you stand up super quickly, you'll notice the opposite. You'll see on the scales that they'll momentarily deflect upwards, giving you a higher weight just for a second, and that reflects that increase in force as you sort of stand up. Now, the type of graphs that you might see in an exam type setting look like this. So let's think about sprinting. Now, at the start of a 100-meter race, this is the start of a 100-meter race, we're seeing this small negative impulse followed by a large positive impulse as we accelerate and increase velocity. That's what we're doing at the start of the 100-meter race. We're trying to accelerate, we're trying to increase our speed. And we do this by our foot actually being in contact with the ground for a longer period of time to generate that speed and power. And you can only do that when you're in contact with the floor to get this large positive impulse. So at the start of the race, when your foot is on the ground for, tiny, milliseconds, tiny amounts of time longer, we're generating more of a positive impulse to increase that speed and that acceleration. So this is what the force time graph would look like at the start of a race if we're looking at the force of the foot on the ground. As the race continues and we get into the middle of the race, we're going to see something that looks like this, where we've got an equal line below and an equal line above the force line there. So those two sort of half circles are equal to each other, and we call this an equal net impulse or a zero net impulse. It's where the line above the zero is equal to the line below the zero. So this is showing us constant velocity. So the runner has hit their top speed and they're maintaining their top speed. They no longer have to keep their foot on the ground to generate that impulse. They've already got the impulse, now they're just keeping it going. And then at the end of the race, this is the last of the three. So at the end of the race, something that you might find interesting to know is that no sprinter crosses the line at their top speed. They all slightly slow down at about 70 meters, I think is the fastest that they get until they start to deaccelerate. So if you look at the splits from a 100-meter sprint, you'll see that. But we can see that there's a large negative impulse and a small positive impulse. So big area under the graph compared to above, showing that the sprinter is now deaccelerating with this negative impulse occurring here. All right, so that was it for the force time graphs. Now we're going to have a look at center of mass in sports. So we're going to look at what center of mass is and how it can be manipulated during different sporting activities. So in the anatomical position, which is the lady on the right here, the center of mass is at the intersection of the body planes. So it's where the frontal, transverse, and sagittal planes meet is our center of mass. And that's when we're in this anatomical position, we're standing upright. Now, depending on how our body moves, that center of mass changes. So in humans, our center of mass is going to vary depending on our body position. And something interestingly is that the center of mass, it's not always inside the body. It might be outside of the body depending on our position. Now, there's a few examples of this. Let's have a look at what you guys do. So in skiing, you're leaning forwards, aren't you? So this, if you're leaning forwards, this is going to push your center of mass forwards as well. If you're leaning very far forwards, it might push that center of mass outside of your body. You're also shifting side to side for your balance and your agility there as well, which is going to cause your center of mass to shift side to side as well. Versus a sport like cross-country skiing, where they're maintaining more of a central center of mass for efficiency and stability. So perhaps they're leaning forward a bit, pushing their center of mass forward, but it's not going to be moving all over the place side to side like in alpine skiing there. So in terms of center of mass, another really good example is looking at the high jump. So we've got two different techniques for the high jump here. We've got the scissor kick and the Fosbury flop. Now the scissor kick, that's like the traditional old way of doing a high jump. You sort of jump up and you scissor your legs over the bar. This requires your body to jump at the same height as your center of mass, because your center of mass is staying around hip level when you're doing an activity like the scissor kick. Now the Fosbury flop, so a guy named Fosbury invented this technique where athletes arch their back to get over the bar. And when they arch their back to get over the bar, what happens is that their center of mass actually lies under the bar. It leaves their body, it's lying under the bar. So they don't need to jump as high because the center of mass is lower. So it's all about center of mass here. So when you jump with a scissor kick, your center of mass is level with the hip. You have to get your center of mass above the bar. Now, the great thing about the Fosbury flop is the center of mass doesn't need to be above the bar. You don't need to create as much force to jump high. The center of mass actually is under the bar. So instead of jumping high, the Fosbury flop is actually more about flexibility. You need to be able to arch your back or arc your back more. So that's why it's become more effective than the scissor technique. If you watch the Olympics, they'll all be, or mostly be doing the Fosbury flop, especially once the bar gets higher and higher. So if it's super easy for them, they might just do the scissor kick to get over. But once that bar gets high, they'll all be doing the Fosbury flop, where they can manipulate their center of mass and jump higher with less force required. And actually, the greater that the athlete is able to arch their back, the lower the center of mass will be. And I've got a video for you to watch on this Fosbury flop technique in your resources online. Okay, moving on now to levers. So levers are important. Levers allow us to move things. Now we have levers all over our body, and we also see levers in day-to-day life as well, and their purpose is to move something. Now we've got 3 types of levers. We've got a first-class lever, a second-class lever, and a third-class lever. And all of these types of levers are made up by the 3 same components: the fulcrum, the effort, and the load. And we're going to see how this is different between the 3 different types of levers, but they're all made up of the same 3 components. So like I said, they can be in the body, muscles attaching to bones, moving loads that we might be holding, or they can be in the real world. All sorts of tools work as levers as well. So 3 parts within the lever system. There's a fulcrum or a pivot point. Now the fulcrum, it's basically the pivot point. It's in the sort of definition. It's the point that's going to move. So the fulcrum, the load is the weight that we're moving. Now in the body, the load could be an external weight, like if we're at the gym lifting weights, that's the load. But also if we're not holding an external weight, if you just flex your elbow, your bicep is moving the weight of your forearm. So it can just be the weight of your body itself that we're moving. And then finally, the effort. The effort is how we're going to apply the force to move the object or whatever it is we're trying to move. And this will make more sense when we see a few examples. So when we think about levers in the body, to make it really easy, I want you to think like this. The fulcrum or the pivot point is always the joint. So the joints in the body are our fulcrums. That's what we're going to move around. That's what we're going to pivot around. The load is always going to be the weight that we're moving, or the weight of our body itself that we're trying to move. And then the effort is always the muscle. It's the muscle that's going to produce the force, but the exact location of the effort is the insertion point of the muscle. Really important to remember that. We'll see that as we move on. So, first class levers. In a first class lever, the fulcrum lies between the load and the effort. So a first class lever, the fulcrum's in the middle. That's how we know it's a first class, because the fulcrum is in the middle. It doesn't matter which side the load and the effort are on, as long as the fulcrum's in the middle, it means it's a first class lever, So we can see in our pictures here, we've got this sort of seesaw example. We've got the load on one side, fulcrum in the middle, effort on the other side, making this a first class lever. And you can see I've written there that there's a trade-off between distance and force. So what I mean by that is, let's take distance as an example. So if I was to push down on the seesaw at the effort, the load would move up the same amount that my hand moved down. So the distance that the load would move is the same as the effort would move. So it's producing the same amount of distance. It's also producing the same amount of force. So let's say the load is 5 kilos. How much effort would I have to apply to move that 5 kilo load? Is 5 kilos of effort. So we've got this sort of equilibrium between distance and force. It's producing the same distance for the same amount of force as well. An example is scissors with that fulcrum in the middle, the load being what we're cutting and the effort being where we actually hold onto the scissors and apply the force ourselves. Now in the body, there's only 2 examples that we need to know. Firstly, it is lifting our head off of our chest. So the load is at the front of our head as we lift it off of our chest. The fulcrum is going to be the joint between the neck and the base of the skull. And then the effort is going to be those extensor muscles on the back of our neck, and they're going to insert on our back. So therefore the fulcrum is in the middle. Another example of a first class lever is the elbow extension from the tricep. So tricep extension or elbow extension, you can write that down somewhere and we'll talk about in class why that's a first class lever. Okay, a second class lever, the load is in the middle. The load lies between the fulcrum and the effort. So second class levers are very, very powerful levers. That's why they're called force multipliers. We can see the wheelbarrow example. So the fulcrum is at the wheel. The load is in the tub that's going to hold everything that we're trying to transport, and the effort is where our hands are going to attach to the handles. So load being in the middle. Now think about it. You can put heaps of heavy things into a wheelbarrow, and you're still able to move that wheelbarrow when you hold onto the handles and you lift it up. You've still got force to be able to move that, even though the load might be very, very heavy. So these are very forceful levers. They're able to produce a lot of force. In the body, there's only really one example that I can think of, and that is standing up on your tippy toes. So when you stand up on your tippy toes, the fulcrum is the joint between our toes and the rest of our foot. So we're standing on our toes, that's the joint that's going to be moving. The load is the weight of our body, which is coming down through the center of the foot, and the effort is coming from the gastroc and the soleus muscles, which are lifting our body weight upwards. The gastroc and the soleus muscles insert into the back of the heel, into the talus bone, right at the back of the heel, therefore making the load in the middle. So there we have a second class lever. Now think about it. If you weigh 60 kilos, you can stand up on your tippy toes pretty easily. You're able to do that over and over and over again as you're walking around day to day. So these types of levers are very, very forceful. They're able to produce a lot of load or a lot of force with very little effort from the muscles involved. Okay, and then finally we have a third class lever. Now third class levers are by far the most common in the body, and they are when the effort is in the middle. So the effort lies between the load and the fulcrum. We've got the effort in the middle. An example would be tweezers, where the load is at the end of the tweezers, what we're trying to pick up. The effort is where we're going to place our hands to pinch the tweezers together. And then the fulcrum is going to be at the end where those two metal parts connect. So effort in the middle, third class lever. Now there's loads of examples of third class levers in the body. Let's have a think about the elbow flexion or bicep curl. So the load is going to be at the end of our limb. It's going to be the weight that we're lifting. The fulcrum is going to be at our elbow joint, and the effort is going to be our bicep brachii muscle. Now, I know you may be thinking the effort is the most proximal, then we have the fulcrum, then we have the load at the most distal. How is this a third class lever? Shouldn't it be a first class lever? No, remember the effort is the location of insertion of the muscle. So we know that the bicep brachii is in the upper arm, but it actually comes down and inserts onto the radius. So you can see how we've got that tendon inserting onto the bone of the forearm. That's the exact location of the effort that we're interested in. So effort being in the middle in this example. Now, third class levers are distance multipliers. They're very good at producing distance, but they're not super forceful. So think about, my bicep. It's not a super, super, super strong muscle in comparison to the gastroc and soleus when I stand up on my tippy toes. But I'm able to move that weight through a very wide range of motion. I'm able to lift it from, by my side up towards my shoulder, and my bicep brachii muscles only contracting not a very long way. So it's contracting to make it shorter, but it's only contracting a little bit in comparison to how much that load is moving. So I'm able to move that load over a greater distance, but it does require quite a bit of effort coming from the bicep muscle. So a little bit of a recap of the levers. First, second, and third class. We differentiate these by what lies in the middle. On a first class lever, the fulcrum's in the middle. A second class lever, the load's in the middle. A third class lever, the effort's in the middle. All you need to remember is 1, 2, 3, FLE. 1, 2, 3, fulcrum, load, effort. If you know what's in the middle, it doesn't matter what's on either side. That will tell you which type of lever it is. First class levers can produce distance and force. Second class levers are our forceful levers. Third class levers mainly produce distance, and they're the most common in the body. And we'll talk about some examples in class. All right, we're almost there. So Newton's law of motion in sport. Hopefully you've got some base knowledge of this topic from if you've done some sort of a physics course before, but we're going to explore a little bit further today. So Newton's first law is the law of inertia. It states that any object will remain at rest or in constant motion unless acted upon by an external force. In simple terms, Newton's first law tells us that an object won't change its motion unless something happens and it's acted upon by some sort of a force. In Newton's second law, it's the law of acceleration. Force equals mass times acceleration. That's our formula there. So a force applied to an object is equal to the mass of the object multiplied by the acceleration. It tells us that heavier objects need a larger force to move them, basically. Lighter objects need a smaller force to move them. And then finally, the third law is the law of reaction. This is the one everyone knows. For every action, there is an equal and opposite reaction. So every action, there's an equal and opposite reaction. Let's have a look at these three laws with some examples of sport. So the first law of inertia. If we have a golf ball on a tee, it will remain at rest until it is hit by the club. So without any sort of force acting upon it, that golf ball will remain there. If there's wind that blows the golf ball up, the golf ball was acted upon by the force of wind or air. Now, once we hit the ball, so we smack it down the golf course, it's going to remain in constant motion until acted upon by an external force. Now, there's lots of external force that will act upon this ball to bring it back down to earth. Otherwise, it would just continue off into the universe. If we took this law at face value, it's going to remain in motion until something happens. So the things that can happen, firstly, we've got gravity pushing the ball down. We have wind and air resistance. If the ball hits the ground and is now rolling along the grass, that's going to produce friction as well. So there's lots of different forces that are going to act upon this ball to change its motion. For the second law, acceleration, we can think about basketball if we're thinking about this law. Remember, force equals mass times acceleration. So if I'm trying to shoot a basketball into the hoop, the mass of the ball isn't going to change, but depending on where I am on the court, I might need to change the acceleration that I apply to that ball. So if I shoot from the 3-point line, and I've done that and I've practiced it before, my body sort of knows how hard to push the ball, how much acceleration to apply to that ball. However, if I shoot from further away, I'm going to need to apply a little bit more acceleration to that ball for it to reach the goal. So super simple explanations here. The third law is a reaction. So the best way to explain this is sprinters coming off their starting blocks. Now, if we take this picture at face value of the sprinters coming off the starting blocks there, and you knew nothing about sprinting, it almost looks as though all these people are about to fall flat on their face, like they're really lent down here. Getting off the starting blocks in sprinting it's a really unnatural skill that needs to be learned. But as the gun sort of goes off and it starts the race for the sprinters, they aren't actually running forwards. What they're doing is pushing downwards and backwards into the starting blocks, which is going to propel them upwards and forwards so that they're racing. So the change in the velocity and acceleration is what's preventing them from falling flat on their face here. But as they push down and back on the starting blocks, that equal reaction that's coming off the starting blocks onto them is actually pushing them upwards and forwards. Now, to continue on from the third law of reaction, we have something called the conservation of momentum. So the conservation of momentum dictates that the momentum before a collision is the same as the momentum after the collision. So the momentum is conserved. The momentum is passed on from one to the next without losing any of that momentum. So if we take pool as an example, we hit the white ball, the momentum is conserved and exchanged into the other balls as they go off into the other directions when it hits them. So momentum's conserved into that white ball that is then exchanged onto the other balls when they hit, and those balls go off in the other directions. And this philosophy comes from the Newton's cradle. So you've seen this before. This is the conservation of momentum. So we, move one ball to the side, it hits the other balls, and then an equal reaction comes out the other end. No momentum is lost. And if you've ever seen one of these, it's very interesting to see how it never stops, because the momentum, it's conserved, it lasts forever. It just keeps going through the balls and coming back out. Another example is in tennis. So in tennis, imagine you're like volleying with another person. As the tennis ball hits the racket, the momentum is conserved and the ball returns back over the net. Now, tennis is a bit more of a trickier example because we can do all sorts of different sort of hits in tennis. But if we're just doing a bit of a rally with someone else, that momentum is conserved within the tennis ball and then the ball returns back over the net. Now, angular momentum in sports is another thing we need to consider. So angular momentum is the product of moment of inertia and angular velocity. So that's a few new words there. But moment of inertia is the tendency to resist angular acceleration. Angular velocity is a rotational speed, and it has a direction term as well. So this would be a vector quantity, but it's the speed in which we're rotating, basically. And then the torque is our rotational force. So let's look at an example to sort of make that make sense. All right, so if we remember, momentum is mass times velocity, and angular momentum is the outcome of the moment of inertia, which is signaled by an I, and angular velocity, which is shown with a W, so it's that rotational speed. So let's imagine a figure skater and she spins with her arms extended, right? When she pulls her arms in, she reduces her rotational inertia and spins faster so that angular momentum is conserved. So in this example, when we've got the arms out, we've got a large moment of inertia, so the arms are sort of resisting that spinning acceleration, and we've got a small W, so she's not spinning very fast. She's not got a very big angular velocity, so she's not spinning at a fast speed. When we tuck in the arms, the inertia, the moment of inertia becomes small, so now she's not resisting the acceleration, and the angular velocity, the W, becomes large, so now she's got a very large rotational speed. You can try this out if you're on a spinning chair and you sort of spin yourself around and let your arms sort of hang out to the side, And you'll notice if you keep your arms out to the side, don't keep spinning anymore, just let the spinning keep going, and you tuck your arms in, what's going to happen is that your rotation will increase, your angular momentum is going to increase. So this is an example of the conservation of momentum. You're not getting pushed anymore by someone. No one's giving you that extra force, but by changing your position and pulling your arms in tight to the axis of rotation, which is your body, we've got that increase in the angular velocity. And when you put your arms out, your moment of inertia increases. It's more difficult to rotate around, therefore reducing the angular velocity. But if you were to put your arms straight back in again, you'd speed up again, and you haven't produced any more force. You've just reduced the moment of inertia, which has increased your angular velocity. So you don't need any more or less force or momentum to change the speed. You can just adapt the speed by changing the moment of inertia, which then affects the angular velocity and how fast you're spinning. We see this come into play in many different sports, such as diving and gymnastics and figure skating, like this example. In any sport that needs sort of rotational control and speed, having an understanding of this is vital. So angular momentum is constant. However, the rotation and what the performer does, they can manipulate the velocity, the angular velocity, and the moment of inertia to either increase the speed or decrease the speed. For example, in a somersault, think about gymnastics now. In a somersault, the athlete's gonna tuck their legs in, and the moment of inertia is gonna be reduced, which is therefore gonna increase the angular velocity. As a diver, let's say you're doing diving where they do lots of spins and things before they enter the water. As the diver goes off the diving board, they do their spins and twists, and when they enter the water, it appears that they're straight going into the water. However, they're actually still rotating upon impact with the water and continue to rotate underwater as well. You'll see this if you ever look up a video or see in the Olympics diving, and they show the underwater shots, that actually underwater they continue to rotate once or twice. So by straightening up before they enter the water, they decrease their angular velocity by increasing this moment of inertia. So they're resisting the sort of turning to get more control of their movement and slow down their rotation. Once they hit the water, the angular momentum dissipates and they're able to stop the rotation. Okay, factors affecting projectile motion. This is our next objective for this module. So projectiles are objects or athletes that are propelled in the air. Anything where someone's going in the air, jumping, throwing something is going to be a projectile. And there's a few important influences on the way that projectiles work in sports. So in terms of influences of projectile motion, we have the height of release, the angle of release, and the speed of release. This is all going to affect the distance or the force that we're able to apply to an object to move it through the world or the air. So the height of release. If we're thinking about this example here, we've got the high jumper and the long jumper. Now the height of release is going to be the same if we're talking about moving an athlete. It's always going to be the floor, right? The person is always leaving from the floor. So in the long jump or the high jump, the height of release, it's going to be the same. It's the floor. You can see that they're both coming from zero height of release there in this graph. If we're talking about the angle of release, a high jumper will leave the ground at a much greater angle than a long jumper, so they're able to jump higher, versus the long jumper who's trying to jump a further distance doesn't need to leave the ground at such a steep angle of release. And then finally, the speed of release. So the speed of release is probably the most influential factor when it comes to projectile motion. speed is directly related to the distance. So the greater the speed, the greater the distance. That's why long jumpers have that big long run up before they jump, versus a high jumper doesn't really need to move that much distance. They only have a few sort of steps or big steps or big sort of like a short run up before they jump. So the greater the speed, the greater the distance. And it's actually interesting when you look at elite sprinters and you get them to do a long jump, they're actually pretty good at long jump. And that's because they can generate that speed from their running that, they can jump quite far in terms of a long jump. If we have another look at a different example now, we've got more track and field sports here. So we've got the javelin in the red line, discus in the green line, and shot put in the blue line. So if we're talking about height of release, they're all sort of generally released at the same sort of height here, which is where our arm is. In the javelin, they might release it a little bit lower as they lean back and throw it. For the shot put, they might release it a little higher as the ball's up near their neck. Now the angle of release, so again with the javelin, if they're leaning back a little bit, they can influence that angle of release. The ideal sort of angle of release is about 45 degrees to reach your greatest distance. And then the speed of release, so again, remember speed is the most influential when it comes to distance. The greater the speed, the greater the distance. So in terms of the javelin, we've got that run up and we're holding onto the javelin for a while to put as much force into it as we can to throw it as far as we can. In terms of the discus, we're holding onto it, we're spinning around and around and around, putting that energy into that discus before we release it and throw it. And then in the shot put, we've got that little shuffle and then the push. Remember, the shot put's very heavy, so it's not going to go super, super far. But we're going to try and release it as fast as possible with as much force as we can from the arm. Okay, our final sort of concept for today is the Bernoulli principle. So the Bernoulli principle, it is an inverse relationship between air velocity and air pressure. I'm going to show you a little demonstration of how this works in a class. But when there's high airflow velocity, the air pressure is going to be low. And when there's low velocity, the air pressure is going to be high. Now, high air pressure always wants to come towards low air pressure. It's just the way that it works, that high air pressure wants to come towards low air pressure. So let's have a look at an example of this in sport. And the best example I can give you is with F1. So let's look at an example of the F1 car. Now, as the F1 car, the great thing accelerates, as the F1 car accelerates, it creates a downwards force onto the ground. It means that the car can speed around corners, and instead of the car lifting slightly off the ground, it's actually pushed back down towards the ground. So we've got this increase in friction and impulse between the tires and the track, which reduces the chance of the car skidding off the track. So the car's like stuck to the track. So what's happening with the air pressure is above the wings of the F1 car, the air pressure is higher, which means the air velocity is lower. The velocity of the air underneath the wings is higher, which creates a low pressure air. Now remember, high pressure always wants to move towards low pressure to keep the car on the ground. So we're going to have the air above the car pushing down on the car to get towards that low air pressure that's below it. So there's a lot of things that go into how this exactly works. I just want you guys to remember that high air pressure wants to move towards low air pressure. So planes work the same. Generally, when you think about planes in the sky, they have high air pressure below the actual plane and low air pressure above the plane. Remember, the high air pressure wants to go to the low air pressure, so the high air pressure below the plane is going to be coming up towards the low air pressure above it, and this keeps the plane in the air. So it's the same sort of principle that's happening there. Now, an extension to the Bernoulli principle is the Magnus effect, and it's the same thing, it just means a rotation around an axis. So, for example, if we have a look at the Magnus effect in sports, we've got hitting the underside of the ball. So in golf, if we hit the underside of the ball, we create an increased velocity on the top of the ball. So we're creating low pressure on the top of the ball, resulting in increased pressure under the ball, therefore forcing the ball upwards as the high increased pressure wants to move towards the low pressure. In terms of soccer, we also see the same thing. So if you hit the right side of the soccer ball, it creates increased velocity and low pressure air on the left side of the ball, resulting in increased pressure on the right side of the ball, therefore forcing the ball to curve to the left. So a bit of a complicated topic there, but just remember, high pressure goes to low pressure, high velocity equals low pressure, low velocity equals high pressure. So we're going to write that down in class and make sure we've got that, but it's how we can manipulate the curve of a ball or the height of the golf ball as we hit it, if we know about this airflow and the air pressure and how that relates to where the object is going to move. Okay guys, that's 4.3.